This is a long question on waves, and in part A, a wavefront is an imaginary line on a wave that joins all the adjacent points that are in phase. In B part 1, we have to take some measurements to figure out what is the frequency and what is the speed of the wave, and therefore we notice that from P to Q there are 3 cycles. So this is the first cycle, then second, and the third cycle, and this takes place in 1.2 seconds. This therefore means that the 3 cycles happening within 1.2 seconds, every cycle will only take up 0.4 seconds, and this is the period of the wave. And to convert period to frequency, we just use the formula F equals to 1 over T to get 2.5 Hertz. Now, speed of the wave can be gotten from the wave equation, but we still need data on the wavelengths of the wave. So therefore, we can actually obtain the wavelength from this measurement over here. This is one wavefront to a second wavefront, and therefore this is the distance of one complete cycle, which is the wavelength, and this is 1.2 cm. And that's how we can obtain the speed of the wave using the wave equation. Now, when you sketch out the graph for C, the displacement distance graph, there are a few things to check. First, check that you have represented the amplitude of the wave to be 6 cm. So over here, all this position should be at 6 cm, and over here, this maximum displacement is negative 6 cm. Okay, next, notice that when we start with a crest, because P represents a wavefront, so let's take it to be a crest. One complete cycle, the wavelength is 1.2 cm. So from a crest to a crest, this distance should be 1.2 cm. And the troughs will happen at half a cycle away, which is over here, and this should be 0.6 cm away. So these are the things that you should check for your displacement distance graph of this wave. Now, part C is a very interesting question about refraction in water waves. So I'll teach you a technique on how we can solve this. So for waves, we can see that there are wavefronts here, okay, and we draw an arrow here to represent the direction of the wave. Notice that this arrow is perpendicular to all the wavefronts, and this arrow also looks very similar to a light ray. So second thing, we must know and memorize this, that water wave slows down when it goes to a more shallow region. Okay, so when the wave slows down, for example, when the light ray slows down, the light ray actually bends towards the normal, as what you have learned in the chapter on light. Same thing goes here. When the water wave slows down, as it changes medium to a shallower medium, the water wave will bend towards the normal. So by right, the water wave should go straight, but because it slows down, I draw the normal and indicated that the water wave actually bend towards the normal. So this is the blue arrow that I just reconstructed. And lastly, I will then recreate all the wavefronts. We must carry on the wavefront, join the wavefronts from all these points over here, and all my wavefronts in orange starts from these points. And these wavefronts are again perpendicular to the direction of motion of the wave, which is what I mentioned just now. So there you go. This will be the complete diagram on how to draw a refraction diagram for water waves. Do learn this and try it out yourself also. Now, once we have the drawing, we can actually solve part 2 in 2 different ways. Without a drawing, we can use the wave equation to argue that the wavelength of a wave, when the speed of the wave slows down and frequency doesn't change, the wavelength of the wave in deeper water will be larger. So when it goes to a shallower water, the wavelength will be smaller because of the slower speed. Now, again, a reminder that frequency of the wave do not change whether it's in the deep water or in the shallow water, because the frequency is determined by the source of the wave. With the diagram here, we can see visibly that the wavelength, which is here in the deeper water, has now decreased in the shallower water, telling us that the wavelength has already decreased when it goes into a shallower water. So there are two ways to solve for C part 2.